Alright, so this is the only video on Google PageRank. This will be a fairly short video. So let me begin by sort of talking about how this is connected to Markov chains, just by looking at a really simple example. Right? Now, for what it's worth, this is the algorithm that was originally used when Google was developed initially by Brin and Page, but the algorithms they use now are much more convoluted. They bring a lot more things into it. There are politics involved, there's advertising involved, etc. But this was sort of the elementary core idea of what they did. So for a little intro, consider this little tiny internet. It's only going to have 4 web pages. So to say internet's a bit not quite correct, but think of web. I'm just going to use that term loosely. Think of it as just web pages linked to one another. So consider these 4 pages linked as follows. So I'll clarify what we mean as we're going. So in the book I've labeled these P1, P2, and so on, but here I'm just going to label them 1, 2, 3, and 4. So consider each of these a web page. And then some of them have links to other ones. So for example, P1 will have a link to P3 and to P2. So those are outbound links that you can click on. If you're on page 1, you can click on a link to either of those two. Page 2 will have a link to page 3, page 3 to page 4, and page 4 back to page 3. So if you look at this, it looks much like a diagram for a Markov chain, like a transition diagram. And in fact, you can think of it that way because the arrows are sort of routing people where they might go. And so in that sense, it kind of makes sense that, like in the Markov diagrams, the steady state was sort of where things would end up. So something that ended up in something like a node that had a higher probability was sort of more popular in a way. So the idea here is that the places, let's say the sites that a surfer, let's say a web surfer, is most likely to end up sort of are the most popular ones. Let me say it that way. So in this case, why not just treat this like a Markov chain, like a transition diagram? So there are a couple of reasons, and we can fix these all and make it work. So one is that there are no numbers here. So first of all, there are no actual probabilities. And 2, this isn't really how web surfers work. They don't just follow links. Sometimes they just randomly jump around, right? Sometimes you don't follow a link from a page, you just randomly load, not randomly, but you choose a page that's not necessarily linked from the page you're at. So web surfers, we'll say web surfers don't just follow links. So this is what they decided to do. So to deal with the lack of numbers is they said, well, look, if a web page has 2 links going out of it, like page 1 in our diagram, web page 1, you could say there's a 50% chance that they follow each of those. But there's also a chance that they don't, that maybe they go to 4 just because they felt like it. So what they said is that we'll do the following. So we'll assign probabilities as follows. Is if you're at a particular web page, so I'm going to sort of bullet this out. So what'll happen is there's an 85% chance you follow a link. And if you do, you choose that link randomly. So 85% chance you follow a link, and if so, the link is chosen randomly. Again, this is not something that is necessarily done anymore, right? There may be more popular links and less popular links, and people may be more likely to choose one link and so on. But this was sort of the basic idea. And then there's a 15% chance that you just randomly choose a web page, and it could be the one you're on. So there's a 15% chance you choose a page at random. Now there's an addendum to the first point, because not every web page has outbound links, right? In our diagram, everything has at least one outbound link, but not every web page does. So if a page has no outbound links, what we do is, because you have to have something there to make it a Markov chain. So if it has no outbound links, you assume it's linked to everything. In other words, literally every other web page. So, for this example, this is what would happen, right? So we'll write down the matrix. So this will be our transition matrix. I want to make sure we have enough space here, right? So there's a 15% chance that it chooses a link at random. Now I'm going to divide this by 4 and multiply it by a matrix of all ones. Now you could think of this as 0.15 multiplied by a matrix of all 1/4, but it's sort of easier to write it this way. This is taking care of the fact that you could randomly jump to any of the 4 pages, including the one you're on, which might be kind of goofy, but that's fine. And there's an 85% chance that you follow a link. So here we have to be a bit careful. So this column is here because if you're at page 1, you could go to 2 or 3, and there's a 50% chance of each of those if you're going that way. Here, if you're on page 2, you could only go to 3. If you're on page 3, you could only go to 4. And if you're on page 4, you would only go to 3. So, just to clarify, this right here, this is taking care of this fact right here. And this other one, this is saying there's an 85% chance that you follow a link, and if you do so randomly. Now, if you notice, when you calculate this, so I'm not going to write down the result. It's in the text, you can look it up. It's not really necessary for what we want to do here, but the point is, because of this first asterisk, this matrix has, this final matrix has no zeros. Hence it's regular. Right, therefore it has lambda equals 1 as an eigenvalue. And we can find an eigenvector. That's according to our theorem that says when you have a regular transition matrix, you can find an eigenvector corresponding to the eigenvalue of 1, and it will have an eigenvalue of 1. So let me clear the screen. I want to write down that eigenvalue so we can see it. I want to redraw the picture, and that way we can judge whether the thing that we've got is meaningful. So the probability eigenvector, so remember how this works is you find an eigenvector. If you do it in MATLAB or something like that, you will probably not get a vector whose entries add to 1. So we have to divide by the sum to make it add to 1. This is what I've got right here. The probability eigenvector is then, I'm going to call this P for a page rank, but it doesn't really matter what you call it, is 0.0375, 0.0534, 0.4711, and 0.4379, which means these are the actual ranks according to the pages, for each page rather. So this is page 1, this is page 2, page 3, and page 4. So what we notice here is that page 3 is definitely the sort of the highest ranked page. It's very slightly more highly ranked than page 4, but page 4 is significantly higher than page 2, which is a little bit higher than page 1. Now, just to make sure that this makes sense, let's go back to the picture. So there's the picture. So let's see that this makes sense, right? So page 3, it makes sense that it's most important because everybody links to it. Right, so this is because every other page, let's say, links to it. Now, clearly page 1 is the least important. This is because nobody links to it. But just for fun, look at the other two, right? If you look at 4 and 2, they both have one outbound link and one inbound link. So they each have one outbound and one inbound. So why is page 4 more important? And if we look up at these calculations, up at the P2 and P4, it's definitely more important. So the reason, and this is what makes this really nice, is that it's because page 3 points to it and page 3 is important. So in some sense, there's a transfer of importance, which makes sense if you think of these as population movement as well. Node 4 will get a lot of results because node 3 does. And if a lot of people are ending up at 3, they may follow that link to 4. So it makes sense that the importance of link 3, of page 3 rather, is transferred over to page 4. So this is why. Whereas page 2 is only pointed to by page 1, which isn't very important. So by comparison, P2 is only pointed to by page 1, which isn't important. Right, so it's always good to have a really important page pointing at your page, right? If the New York Times links to your home, to your personal website, that's fantastic. But if some obscure website links to your website, that doesn't matter so much. So here's one more example. I want to do one more that has an internet that for which one page has no outbound links. So we'll do the same arrangement. I'll just do 4 for now. And the links will be a little simpler, or a little similar, but not quite the same. So 1 will point to 2 and 3. 2 will point to 4, which points back to 3. And 2 points to 3. So the big difference I want you to note here is that number 3 has no outbound links. So what we do in this case is we assume that it links to everything. Otherwise, when you write the matrix down, you will not get a stochastic matrix. Your column will not be right. So when we do this one, we still have the 0.1504 with all the ones. But now what happens when we do this 0.85? Page 1 could go to 2 or 3. Page 2 could go to 1 or 4. Oh, sorry, to 3 or 4. Page 3 now we assume it goes to everything. So that's why that's there. Everything else is just fine. Page 4 links to page 3 only. And then we can do the same thing here. And we get a page rankings of 0.1347, 1919, 4572, and 2162. And here again you can see that page 3 in this case also is the most important. It has 2 things pointing to it. Number 2 has 2 things pointing to it, but one of those is number 1, which isn't that important. So again, it makes sense in this regard. All right, so last thing, let me clear the screen, write down the general rule so we have an idea about how to build this matrix in general. I'll make one closing comment and then we're good. So here we'll say general matrix. So this is if we have n pages. So the matrix will look like this. You'll have a 15% chance divided amongst those n's. This is an n by n matrix of all ones. And then we'll have 0.85. This is the 85% chance that you follow a link. And in here we have a bunch of vectors. We have n of them. And what we say is that v sub I is determined as follows. So if page I has outbound links, let's say has k outbound links, then those targeted pages or rather let me say it this way, the rows corresponding to those targeted pages is maybe a better way of putting it. Let's say the rows corresponding to those pages each get 1 over k. So for example, if you link to page 2 and page 3, then the second and third rows will each get 1/2. And if page I has no outbound links, every row gets 1 over n, and everything will work. And then this will be regular. We find the eigenvector corresponding to lambda equals 1, which is guaranteed. We scale it. Now, for what it's worth, because you're just scaling it, in theory you could argue that they would be relatively speaking, the values would still count even if you didn't scale it. But to be proper, we would scale to be a probability vector by dividing by the sum. Now, as a closing note, this is sort of a computational note, is the only actual calculation that you need to do here, right? You need to find t. That's easy. Now, for what it's worth, it's not really easy in the sense that if the internet has millions of pages, this is a lot of work. But the way that Google does this is they're continually trawling the web, crawling through, checking links, so they're constantly getting new data about this. So to say find t is easy, it's computationally, like, it's not difficult to express how you do it. It might take a lot of time, might be slow, but it's not difficult. Now, you don't need to prove that t has an eigenvalue of 1. That's not a problem, right? So the fact that t has an eigenvalue of 1 is guaranteed. So the last thing you need to do is you need to find the eigenvector, which means you need to solve tv equals 1v, which is the same as solving t minus I v equals 0, which is basically just solving a linear system, which is giant row reduction. Which is not hard, right? Which is, again, easy, right? Which is not to say it doesn't take some time, but it's easy to do, right? There's nothing, if you needed to find the eigenvalue, that would be very difficult because that involves solving a massive polynomial. That doesn't just take a long time, it's actually computationally difficult, it's mathematically difficult. So the point is that the things we have to do are actually mathematically easy to do, even if they take a long time. So I'm going to call that done. Again, the way that Google works has changed a lot since then, but this was, and to some degree still is, the underlying algorithm. It's sort of imparting importance and rank on pages that other pages point to. So that is that.